that recording. Okay, so the last section on chemical calculations, and that's what we're doing here, is on acids and bases. Acids and bases really are kind of an extension of the unit we just finished on solutions, because it turns out that acids and bases, in order for them to behave as acids and bases, have to be dissolved in water. So we must have an aqueous solution of the acids and bases. So let's first talk a little bit about properties of acids. Okay, and this is stuff that you've probably seen in the past, probably in grade 10. Your grade 10 teacher should have gone through some of this stuff, so it is review. But this is just a list of properties that we find that acids all have. I did a little bit. I've added in there a list of common acids and bases. What are you looking at? You're looking at making acids and bases. That's tomorrow's.
Oh.
That's not today. I put tomorrow's up just because I did it this morning so I wouldn't forget. And it does say tomorrow, doesn't it? It says Friday? Okay. Okay. Yeah. So all acids have a characteristic set of properties. They taste sour. I'm sure you've all tasted various types of acids. Vinegar is a prime example of an acid that I'm sure you have tasted, either on French fries or perhaps by itself, or salt and vinegar chips. And things like lemon, right? Again, very sour. They change indicators a characteristic color, all right? So some common indicators that we use is litmus paper. And if you dip litmus paper in an acid, it becomes red. All right, so litmus is red in an acid. Here I've got some various types of indicators. I brought two indicators to this class, but I didn't get to using this one. This one's called phenolphthalein. Phenolphthalein we're going to be using in these experiments coming up. These are, phenolphthalein is colorless. It actually doesn't have a color in an acid. This indicator that you're looking at here in the giant test tube is called universal indicator, and it's actually a mixture of a whole bunch of indicators. So what the universal indicator has been designed to do, it has been designed to change a specific color depending on the pH of the solution. I was telling you as you came in that the yellows and reds are acidic. They tend to be acidic, and the blues tend to be basic. But you can see there's a definite purple in there, and then you can see now I've gone from the red, it's turning a little yellowish, right, with a little bit of green. The green is neutral. It looks like in this mixture that I've made that the base is winning out over the acid. But if I could pick out a little color, it would tell me what the pH is at that particular region. So the deep blue tends to be a quite low pH, or sorry, a quite high pH of around 11 or 12, where a deep red is a very low pH because that's the acid color. So this universal indicator is a mixture of indicators. They react with metals to produce gas. So if you take a metal and you put it in an acid, it will bubble away and it'll produce hydrogen gas. It'll pop, all right? An example of that, the internet and Facebook is always great for entertaining stories, but some of them, they do have a basis to it. You might have come across things about Coca-Cola or things about, carbonated beverages. You'll never drink it again. You know what I mean? And then, you might come across something that, you can dissolve a nail in Coca-Cola. Well, there's some truth to that. You can react iron with the acid that's in Coca-Cola in order to react it away. Now, you'd have to keep putting new pop in because the acid that's in pop is very weak. So it would take a very, very, very long time, and you'd have to keep adding new pop. You'd have to put it into a new, nice, fresh glass of pop because once the bubbles are gone, it's not an acid anymore. But you could do it. It just would take forever, right? And that's the reaction there. They react with carbonates to produce carbon dioxide gas. We'll talk about these reactions a little bit later on. But that particular reaction is the vinegar and baking soda reaction. If you've ever watched any Disney, have I talked about this already? If you watch any Disney show that involves kids, you know what I'm talking about, like The Sweet Life, right? You would have been a big fan of The Sweet Life, right? What is it, Zack and Cody, I believe, right? Okay. Anyway, or you could pick whichever. Again, we could talk about the cartoons. I know I saw this on Recess. Anybody remember Recess? Some good stuff, right? If you have any Disney show and they're doing a science fair, there's always going to be this in the science fair. What am I talking about? The volcano, right? You've all seen the volcano. And whenever you have it on a Disney show, it goes horrifically wrong, and everybody ends up covered in some kind of colored foam in some way, right? We've all seen that. Well, that actually is a reaction. If you take vinegar, the acid, and you mix it with baking soda, which is a carbonate, it's sodium bicarbonate, that reaction produces lots of carbon dioxide gas, lots of bubbles, and it foams over, and that's what gives the volcano the foam. Add a little bit of food coloring to that, and you get some kind of colored foam. All right, and that's what that reaction is. They are electrolytes. So acids will conduct electricity. So if you had a conductivity apparatus, remember our little conductivity apparatuses we used at the beginning with the little LEDs? We tested them for ionic compounds. The ionic compounds turned on the light. Well, acids will also turn on the light as well. They have a pH of below 7. Again, depending on who your grade 10 teacher was and whether you looked closely at acids, right? You would have recalled, we would have talked about the pH scale, and acids then have a pH less than 7. And they all dissolve in water, all right? They're soluble in water. So if all acids have all of these properties and they're the same, then they must have something in common about them, all right? And that's what we want to look at today. Before we look at the definition for an acid and what that thing is in common, let's talk a little bit about some common acids, just to get you guys to think about maybe where you've encountered acids before. And yeah, let's write a few of these down and just make a note of them. So this is where I'm asking you, where would we come across an acid in your everyday life, that type of stuff? What do you got? Sorry? Bleach is not an acid. That's for my next list. Bleach is a base. It is. It is a very common base, and we'll talk about that in a moment. An acid, I've actually mentioned 2 of them so far in the discussion. Oh yeah, you were ahead of the game. Battery acid, that's correct. And what else? I said lemon as well, didn't I? Okay, let's go with the battery acid first. Common source. So I'm going all the way to the common source. Battery acid, and I'm going to go with a car battery, all right? Different than a regular battery, a car battery. And the acid that's in a car battery is actually phosphoric acid. And its formula, we haven't done the naming of acids yet, so I'm going to tell you, is H3PO4. Excellent. How about another acid that you might know of, common acids that might come across? Yep. Goodness gracious. Chloric acid, that is a type of acid, but I don't know of a common use of chloric acid. What I will do is I'm going to adjust yours a little bit to change it. There is a common acid that we use a lot of, and it's hydrochloric acid. Now, hydrochloric acid is a little different than chloric acid, and we'll learn about that when we learn about naming acids and bases after the break. And its formula is HCl, all right? That's hydrochloric acid. And common use or a common source, if you have a swimming pool, you might use this. If you, again, in terms of reacting with metals, my dad used to have a little trucking company that would truck pigs to market. So you know those trailers that have the holes in them so that they can stick their cute little snouts out and everybody says, oh, poor little pig. All right. No? All right. Anyway, My dad used to clean the trailer with this acid, with a solution of hydrochloric acid. So if you go to a pool supply store or perhaps to a farm supply store, you can purchase muriatic acid. So the common name that you would encounter if you just went out and purchased some would be muriatic acid, all right? And that's used for changing the pH in a swimming pool if you're trying to open your pool up and you got to get the pH right, or sometimes you can use it for cleaning, you know, that type of a thing. Yeah, muriatic acid you would add to change the pH. The chlorine puck is creating a chemical that kills bacteria. Two separate chemicals doing two separate things, all right? And actually, the chemical that the chlorine puck produces is related to what's in bleach, and we'll talk about that when we get to the basis. Any others that you can think of? Any other acids? Well, I've already talked about vinegar, vinegar, got to say it that way or you'll spell it wrong. And it's what's called acetic acid, and its formula is H, and now I got to think about that ion. I don't usually write it this way. HC2H3O2. All right. That is hydrogen on an acetate. An acetate is on the back of our table. So vinegar is obviously vinegar, right? We can use it to make pickles or, you know, make your fries taste awesome, or if you like that type of stuff. All right, and let's just put a couple more here then. Ascorbic acid. Ascorbic acid. And to be honest, I don't know what the formula is. It's what we call an organic acid made by many chemicals. You could track it down if you'd like. And since you're looking it up, what is ascorbic acid also known as? I'm waiting for you guys to access Google and have Google inform us what ascorbic acid is.
I believe it's
C6H8O6. And does it have another name for it, a common name for it? What is ascorbic acid? No, don't worry about images. I may be wrong. I might have been quoting this wrong for years. I might be learning something here. I'm pretty sure it's vitamin C. I'm pretty sure ascorbic acid is vitamin C. Look up citric acid. That's not vitamin C. Citric acid. Where do we find citric acid? Yeah, citrus fruits, right? Citrus fruit. Uh-oh, forgot the R. Worried about the U. I got it. Fruits. Got to say it that way. You spell it wrong. Why would you need an I in there if it's called fruits? Really, come on. Darn English language. Do you have a formula for citric acid? What is it? Oh, how many O's? Oh, that's exciting. They must be really close to each other and related to each other. Yes, but the citrus fruits also contain the ascorbic acid, which is the vitamin C. For which ascorbic? Whew. Well, I just feel good. I feel I've been telling lies for years. Apples contain a lot of ascorbic acid. It's not one that's kind of as fashionable as the oranges during the winter. Eat lots of oranges, but you can get lots of vitamin C from apples as well. Apples are quite tart as well, right? So they've also got a quite high acidic content. Excellent. What's that? Caffeine in apples? I don't know. I can't dispute it. I don't have knowledge for or against. All right, let's continue. All kinds of acids. Now, I was hoping we could see what's common with all of these acids, but my last two have kind of messed me up. They've messed me up because they've put the H in here. But if you notice, all of our acids start with H. And if we looked a little closer at this formula, it would probably be better represented if we had an H in the front and we had 7 over there. You see what I mean? One of the H's in front. Same with here, an H in front and a 7 over here. Because again, it is the H that is in front of these molecules which makes them behave as acids. So let's officially write down the Arrhenius theory of what an acid is. Now, Arrhenius, you know, for a spelling challenged person like myself, Arrhenius is very painful. I get it wrong every time. Arrhenius. Arrhenius was a scientist that lived around the mid-1800s, and he, one of his contemporary scientists that lived at the same time, his name was Faraday, and Faraday is credited with discovering ions, right? We know what an ion is. It's a charged atom that's either gained or lost some electrons, and Faraday was studying the ions as they floated around in a solution. Well, Arrhenius extended that and realized that when a solution contained the special ion H+, then they exhibited acidic properties. They were all acidic. They tasted sour, they changed litmus to a different color, they were electrolytes, they could react with metals, they could react with carbonates. So we now believe that it is the H+ that is responsible for making acids behave the way they do. So what do? Acids are molecules which ionize in water to produce H+. What is an ionization reaction? It's a reaction when an electrically neutral molecule produces ions. We're going to do some examples here in a moment. How do you detect an acid? If you're looking at the formula, the chemical formulas generally begin with H. There are some ways in which we write them where they don't put the H in front. We saw that with our last 2 examples, so it becomes a little trickier to determine whether they're an acid or not. But that's what you're going to be looking for. Okay? So right now we're going to do some ionization reactions. We have already done reactions called dissociation, where the 2 atoms fall apart when they dissolve in water. This is the same type reaction, except we're going to be starting with a molecule instead of an ionic compound. Just waiting on a few writers here. We're good to go? We're good to go? Okay, so let's do some ionization reactions. From this morning. What are you looking at? My base examples? Oh, the test tube. It means I haven't added enough acid. I should have my goggles on. I mean, I do have my goggles on. Okay, let's take a look over here. I shouldn't have put that in there. Let's look at this. So take a look. This is a metal, sorry, this is a nonmetal and a nonmetal. This is a molecular substance. When a molecule goes into water and falls apart to produce H+, there it is there, aqueous. And now we're going to be left with Cl-, aqueous. This is what we call an ionization reaction, okay? Let me illustrate what's happening in this reaction. We have an H that's bonded to the Cl. There's its molecular structure. When it goes into water, this pair of electrons leaves the H and goes to the chlorine. That's going to give chlorine all 8 of these electrons. When chlorine has all 8 of the electrons, it becomes chloride. So we get that right there. The H now is missing its electrons, which means it becomes a positive charge, and we get that right there. So the molecule is literally ripped apart as it goes into the water, called ionization. It's become ions. It started as a molecule and then becomes ions in the end. I'm not going to draw that picture for all the rest. I'm just going to do the ionization reaction. So there's my hydrogen right there. That's going to come off. H plus, aqueous. The negative part is going to go with the nitrate. NO3 minus, aqueous. And we say ionization has taken place. Okay? Again, here's my hydrogen. That's going to fall off. H plus falls off. The electrons go with this thing to make it negative. C2H3O2 minus aqueous. All right? Okay? Again, these are all molecules because they're all nonmetals. All right? And they become ions, and so it's called ionization. So acids are molecules that ionize to make H plus. It is these H pluses that is common in each, and that's what turns, you know, the indicators different colors and taste sour and all that stuff. All that stuff is due to the H's. All that stuff. All those properties. It doesn't settle because it's a solution. It would diffuse and mix because of the stirrer. We'll play with that later on. I'm not going to pour any in right now because I want you to watch me instead of that. It is. I'm going to have to get some out. I'm going to need a hose of some sort. Okay. Are we good to continue? Because these two obviously are ready to continue. We good to go? No. I'm going to go with Amy Jean, even if it isn't correct. Don't write that down. I think we get that idea. It is the H plus which is responsible for the properties. All right. Actually, you know what? I do want you to write the second bullet here, starting right here from this bar right here. The more H plus, the more acidic the solution is. So please write this statement down starting from here. Start from there. All right. The more H plus there is, the more acidic the solution is. So if we were to dump lots of HCl into some water, we would get lots of these H pluses, and it would be more acidic. Should we write that down? I don't need the first bullet, because I think the first bullet we know. The H pluses, that's what makes, you know, the acids behave their way. But the more H pluses there is, the more acidic the solution is.
Wait. Just right? Like the H no, and then like acid.
Yeah. Yep.
If would be more than one H plus at the beginning, would it be?
No, I'm talking about adding lots of this to a solution, like a highly concentrated solution. So if I dumped a little bit of HCl into some water versus a lot into some water. If I had a lot of it in there, poured a lot of it in, then I'd have lots of these, because each one of these molecules would produce an H.
So if it's not the H, but like the molecule side?
Yeah.
If that were to have like more H's than the most bitter?
That's a very complex situation. In the grade 12 university course, we talk about what happens when there's more than one H that can fall off. And we have to treat each one separately. And I will talk more about this a little bit when we get to Monday's lesson, when I talk about strengths of acids and bases. Because you're probably well aware that we have some acids that we would consider strong, that can be dangerous, and some acids that are weak, that are not so dangerous. And so you're getting ahead of the game a little bit, and we'll discuss this on Monday. All right? But if something can produce lots of those, then it's very acidic. Okay, let's talk about bases. All bases have a characteristic set of properties. Here are the properties for bases. Many students sometimes think that bases are just opposites of acids, but they really aren't opposites. They do have their own specific set of properties. And they can react with each other to cancel out their acidic and basic effects. That's what we call neutralization. But that doesn't necessarily mean that they're opposites, like true opposites, like black and white and, you know, things like that. They do have the ability to react with each other and cancel out their acidic and basic effects. They taste bitter. Have you ever tasted a base? Baking soda is a base. And baking soda, if you've ever, you know, some people say you can brush your teeth with baking soda, and that can be used as a tooth whitener, much cheaper than an expensive, tooth whitening, whatever. So you can actually brush your teeth with baking soda. I tried it once just because I wanted to see what it tasted like. And it's disgusting. It's very bitter, absolutely disgusting. You can actually buy toothpaste with baking soda in it. And it's bitter too. You think, hey, this is awesome. I don't have to, it's bitter. I can't think of any other bases that come to mind. That's the one that I know I've tasted. Yeah. Now, slippery in texture, many cleaning products are also bases. If you've ever used Fantastic, like that's what I just used to, clean up or if you've ever used window cleaner like Windex or something like that, they contain a base. And when you're done, if you've ever washed your hands, which you should do after you're done, cleaning, you'll find your hands are slimy and slippery. And that's because they contain bases, right? And so they're slippery and slimy because of that. Soap contains a base. And it's not a very strong base, but it contains a base, and it is slippery as well. They change indicators a characteristic color. Litmus is blue. The phenolphthalein becomes this beautiful magenta or fuchsia. Some people say, I think it looks pink. Looks pink to me. Anyway, and we'll be using this in our experiments. The universal indicator we've seen turns a purple, a deep purple for a base. Okay, they're electrolytes, which means they'll also conduct electricity. You'll notice that's not opposite to an acid. So both acids and bases are electrolytes. And they have a pH above 7, towards 14. And we will look closer at that as we get going. Again, there must be a common atom or group of atoms that gives them the same characteristic properties. What do you think? No, you could, but we're gonna be talking about that common thing in a moment or two. Now, bases are a little trickier than acids. We're going to only learn about the Arrhenius theory of bases, and they're a very simple theory. We're going to talk about here in a moment examples of bases that don't follow this theory. That means the theory that we're learning for this course is a simplified theory of bases. We can explain the complex bases that we're going to write down, but we would need to teach you about a more detailed theory, which we don't cover in this class. Tomorrow, because I taught this lesson to my grade 11s, tomorrow in the grade 11s, I'm going to teach them about the next step of the theory, which is called the Bronsted-Lowry theory of acids and bases. And they will have to explain those more complex bases. We are not doing that in this course, but we're going to come across them here in the list. Let me give you some bases that do follow the Arrhenius theory first, then we'll talk about these other ones that are a little more tricky. So here's examples of some bases that do follow the theory we're going to learn about. NaOH. And I'm gonna put in the name and then the common source here in a moment. Another one that is common, that you can find, that follows it, MgOH2. And we'll talk about what that is. And another one that you find in your household, if you go looking close enough, NH4OH. Now, all of those follow the theory that we're going to look at. And what is common about all of these examples of bases? Yep. They have OH, which is called hydroxide. So the names, this is sodium hydroxide. And what's this one here? Second one. Magnesium hydroxide. And the last one? Yeah, ammonium hydroxide. Ammonium hydroxide. And gee, what's the common feature of them all? The hydroxide is. And that's the theory that we're going to look at. Common sources, where you can find sodium hydroxide in your home. You've already done some looking up. What? Drain cleaner. Drain cleaner. Normally, if I'm cleaning the bathroom or cleaning the house, and it says on your, on your Windex or whatever, wear rubber gloves. I used to say, forget about it. Rubber gloves, I don't need rubber gloves. But if I'm going to use drain cleaner, I'm going to wear rubber gloves. Because drain cleaner has very, very concentrated sodium hydroxide, like dangerously concentrated. You actually should be wearing goggles too when you're using that particular type of chemical. Because if you're pouring it down the drain, a little bit of it were to get into your eye, that would be a really painful thing. All right. Magnesium hydroxide. Nope. Magnesium hydroxide is not window cleaner. Actually, is it really? Really a laxative? Oh, that's not what I would think it would be used for, but hey, that's good to know. Anything else for magnesium hydroxide? Antacid. It's an antacid. You can buy this in the drugstore. It's called milk of magnesia, and it is an antacid. And why do you take an antacid? To get rid of your acid. To get rid of stomach acid. Right, so let's say you you ate too much Christmas, and you got, acid reflux, take an antacid. What's that? Tums, but Tums uses a different version. It doesn't use that, all right? The reason it's called milk of magnesia is because really the magnesium hydroxide is a fine powder that's mixed with water, and when you shake it up, it becomes kind of milky, and then it settles back down. Ammonium hydroxide. Yeah, this is general cleaner, window cleaner, general, you can use it just as a general cleaner. I'm going to put here window cleaner. The ammonia, you don't want to, be immersed in a strong concentration of ammonia, but you've probably smelt ammonia before. If you use the window cleaner, it's got a distinct odor. It's kind of a piercing odor. If you've not, like the Windex tries to cover it up with some perfumey stuff, but you can buy not pure, but you can buy a solution of just ammonium hydroxide. Like it's really cheap and it works great for cleaning windows, but it doesn't smell pretty. It stinks quite badly, but it works great for cleaning. If you've ever, watched professional sports and they're sitting there getting ready to play the hockey game, and before the game, the trainer comes along and they give them this little thing and they break it open and have you ever seen they smell it? Like they call them smelling salts, and they all, they all kind of perk up. They tend to have concentrated it's like a swab that's got some ammonium hydroxide in it, and it just wakes you up. It smells so bad. Yep. So that's where it's used there too, but that's typically not, Toilet bowl cleaner probably has some bleach in it. Yeah, I would think. Okay, so notice how they all have hydroxide. Let's now talk about some bases that don't have this, which we're not going to explain, but bleach. So bleach is NaClO. This is called sodium And this is a hypochlorite, all right? Sodium hypochlorite. And bleach is a quite concentrated form. Again, should have goggles on, right? You know, if I'm doing whites, right? I'm doing the laundry, doing whites, and I want to add some bleach. Normally, I just take the jug, open it up, and pour it in, right? Have a big old look at it. And every once in a while, a little drop will come back at me, and I'm like, should maybe have some goggles on there. But that'd be pretty geeky, wearing goggles to put some bleach in the washing machine. But it's pretty strong. Hypochlorite, this part of the molecule right here, that part of the molecule is what is created by chlorine pucks in a swimming pool. All right? So the chlorine pucks undergo a little chemical reaction with the water. That creates the hypochlorite. And then the hypochlorite goes around and sticks to the bacteria and whatever's trying to grow, the algae. And for some reason, it prevents it from growing. It kills it. All right? You're essentially putting bleach in your pool. You could use bleach, but the problem is when you dump bleach into it, you're dumping a lot into it. The amount of hypochlorite goes up. Somebody goes for a swim, they come out, they're all itchy and rashy, and their eyes are as red as can be, right? And then it gets used up, and it goes down, and it's gone. The puck slowly produces the ClO, slowly producing it, keeping it at a nice, steady level for a long time to kill the bacteria, but not to have it so concentrated that you're burning everyone's eyes out. They probably do. In big pools, they will probably have some kind of a dispenser that just dumps bleach into it. Well, it slowly lets it in or something like that, an expensive way of controlling it, right? But you'd save money because bleach is cheap compared to the pucks, right? Okay, and let's just talk about one other, and that is baking soda. Baking soda, like I said, we already came across baking soda. It is a carbonate, so it can produce carbon dioxide, but it is also a base, NaHCO3. It is sodium bicarbonate. Sodium bicarbonate. And I already said if you brush your teeth with it, right, it tastes sour. But again, notice, sorry, tastes bitter. You're right, tastes bitter. But if you notice, there is no hydroxide in those. So in order to explain why these are basic and why they behave as bases, I need to teach you another theory, but that's not part of this course. But if you'd like to go and enrich yourself, you're looking up Bronsted-Lowry theory of acids and bases, and that would explain it. I have no idea. I don't know why it would be a base. It doesn't eat the rust. It lubricates, but but not all slippery, slimy things are bases. Bases are slippery and slimy, but not all slippery and slimy things are bases. Do you see the logic? So things like WD-40 are based on oil-based products, so they're slippery because of the properties of the oil, right? So the Arrhenius definition of bases. According to Arrhenius, what did he consider a base? Well, they're ionic hydroxides, which means they have to have a metal on the front and a hydroxide on the end. And they dissociate in water to produce the cations, whatever's with the metal, and the hydroxide. We've already seen dissociation. Dissociation is when something that is ionic to begin with simply goes apart. So in the next slide, we will do some dissociation examples. Again, finished?
Yeah. Am I missing something?
I don't understand how.
No, and I've changed the marking scheme on that
Okay,
big
good.
time. Yeah.
You should have told me that before I.
Oh, that's, no, stress is good sometimes, just little bursts of stress. No, you're right, stress isn't good. I'm bringing on some premature aging by forcing some stress. No? Oh, all right. Okay, so I have no idea where everyone's at. Are we done? Are we ready to go? Good to go ahead? Various people are on different slides. So now we're just doing some dissociation reactions. Now, this can be confusing, but I'm going to try to show you how to get it right. This thing right here is ionic, where HCl was molecular because it's made up of two nonmetals, right? This is made up of a metal and a hydroxide, so it's ionic. It's going to separate into Na plus and OH minus. And we call it dissociation. And that's what gets students all mixed up. Ionic things don't ionize. They're already ions. They don't have to become ions. Molecules have to ionize. Ionic compounds just dissociate. They go apart from each other. If I were to draw the picture like I did for HCl, if I were to draw out NaOH in terms of their electrons, Na has already given away its electron. It's gone. OH has already accepted its electron. So OH is already negative. They already exist as ions. They don't have to break the bond. So they just dissociate from each other. Okay, and that's the difference. Let me give you another example. Let's say that you and your friend, good friends, right? You're attracted to each other, opposite charges. You see how that works? And for some reason, your friend doesn't reply a text or doesn't do something, and you've had enough with that friend. And you simply say, all right, that's it. I don't want to associate with you anymore. I am now dissociating. And I think I talked about that in a video, right? Where then I said, you go that way, I'm going this way, we're dissociating, and away we go. No need to have any formalities, just dissociate, all right? Let's say, and let me now contrast this with what we did with the acids. Let's say we had something like HCl. Now, HCl is different. That's like two friends that can't keep their hands off of each other. You know what I mean? They're always holding hands. They're always, you know what I'm talking about. They're always together. So that type of breakup would be a little more complicated, right? So imagine one of the partners says, okay, that's enough. I think maybe we should go on our own ways. And let's say the other partner says, no, and hangs on real tight. In order for that breakup to happen, there needs to be an extra step. Let go of me, let go of me, all right? So once that process takes place and they're alone, then they can go. So you can imagine with this, we've got to have a breaking of a bond in some way. We call that ionization. That's why this is ionization. They need to break first, and this is just dissociation. They just have to go on their way. They don't have to break anything. Okay, so that's the difference there. Let's keep going and finish these off. So in this case, I'm going to have Mg plus aqueous. Actually, I'm going to have Mg plus 2, because if we check the charge on an Mg, it's plus 2. And I'm going to have 2 OH minuses. Now, we did this when we did our net ionic equations. We've done this type of process. Here I'm going to have an NH4 plus and an OH minus. Aqueous, aqueous. I do want you to write this whole thing down. It is or at least maybe from here, like we did the last time, the more OH minus there is, the more basic it is. I think we get the idea that it's the OHs that are doing the job here. Yes, I'm going to go through right to the end so you can keep writing. Okay.
What?
It doesn't dissolve in water, so it wouldn't have a pH associated with it, right? It's got to be dissolved in water to be an acid or a base. So we have the OHs that are responsible for the base being the base. To finish off, I have to talk about what, if we've got acids and bases, what about neutral things? What do we have if we have something that is neutral?
Is it like magenta or something?
What are you talking about? That's the phenolphthalein. All right. Am I good to go here? I don't know where anybody's at. I have no idea. Okay. So, properties of salts. Salts are substances that are not acids, nor are they bases. They are ionic compounds. When they dissociate, they don't produce H pluses, nor do they produce OHs. Notice it says salts, and it doesn't just say salt, which is what we associate with table salt. Table salt is sodium chloride, and that's just one example of many types of salts. Any ionic compound that is not an acid, that does not have the H plus, nor is a base, does not have the OH minus, is considered a salt. So you can see my examples down there, KCl and magnesium bromide, MgBr2. They taste salty, which is a terrible definition. They don't change the color of indicators. They are electrolytes because they form ions. And they have a pH that's equal to 7. They are neutral. Salts are ionic compounds that dissociate, that produce cations that are not H plus, and anions that are not OH minus.
And that's the question I haven't been able to answer on the test this year.
Exciting.
No. I thought I did terrible, but my marks went up by more than the last test. Sorry, we'll stop talking. Keep writing. I know. I'm still talking. No, it's just boring. I don't like it.
Well, the sooner we get done writing, the sooner I get to play with adding more. Mm-hmm.
I like it better.
Alexis is waiting patiently to advance, people. Am I advancing? I have no idea where everybody's at. Molecular substances, so regular molecules that are not acids are also neutral. It is. When we get to the beginning of a of a chapter, we've got a lot of defining and explaining to do. That's just the way it kind of goes. Keep writing. So, molecular substances. The example I have here is, I think this is a glucose molecule, so like a sugar. They do not have the ability to lose their H's. Again, notice we don't have an H in front. I know with those ones we got online, they didn't put an H in front either, but I like this representation here. There is no H in front, so all of those things are stuck together. They're not going to lose an H. If I ask you to identify whether it's an acid or a base or a molecule, I will put the H in front to let you know that it's the acid. That's the way you're going to be able to tell. Is there an H out front? This molecule does not have an H out front. They do not change the color of indicators. They're non-electrolytes because they don't fall apart in the water. And they have a pH of 7. They contain all non-metal atoms. Let me give you an example, a better example of, well, not a better example, another example of a molecular substance. CH3OH aqueous. All right. Actually, I could have put liquid. When it dissolves, it stays together. CH3OH. You might think that that OH on the end is a hydroxide, but it doesn't fall off. Why? Because these are all non-metals. They're all on that right-hand side. The structure for this thing is like this. CHHH. So it's got the 3 H's bonded to the C, then the O, then the H. That OH is stuck tight. Remember how I said ionization of a molecule is kind of like a breakup of that couple that can't keep their hands off of each other, and finally someone decides that maybe they should keep their hands off of each other? Well, this molecule here is like the couple that doesn't break up. The bond between those two things are so strong, you dissolve it in water, they don't fall apart. They're that they're that high school sweethearts that make it right to the end. It's beautiful. Anyway. No? My analogy is good? Bad? Okay. All right. So this breakup can't take place. It doesn't fall off. It cannot. Sorry? Again, I'm hit and miss on your little mumbles. I don't know whether they're significant or not. Not significant. Excellent. I'll go on because it's not significant. Okay, now don't write this down. I've got a big example for some practice because there is a sheet, and just write down that, but don't write down the grid. Just write down the type of substance, type of solution, ionization or dissociation reaction. And I will go through this. I'll go through this one by one with you, and this then guides you on how you're going to do this little assignment. No, a little worksheet, little practice sheet. I'm going to mark marks. The only one I'm going to mark. Because then you'll do it. No. Okay. So, type of substance, cesium and an OH. Amy, I'm giving you the first one. Then, what's that? Type of substance. Actually, I want there whether it's ionic or not.
It is.
Hold on. I'm fixing the periodic table here for a second. But I'm not ready to write it down. Oh, that was terrible, wasn't it? Why didn't I? Okay. No, I just pulled on too much. There we go. Okay. Gentle. Okay. So, cesium And the hydroxide. It is ionic. Ionic. When it gets dissolved in water, will it be acidic, basic, or neutral? Yep. Basic. This is your only one. Basic. How do you know that it's basic? Because of the OH. How do you know it's ionic? Metal, the metal and the hydroxide. Good. So the metal here and the hydroxide tells you that it's ionic. What type of reaction will it undergo? Amy? Dissociation, because ions just have to dissociate. They're the non-huggy kissy couple. They're just the one that hang out with each other, you know, like the nervous ones that keep their hands to themselves. Dissociation. Dissociation. Okay, and I wanted green on that. That's okay. FeCl3. What type of substance is it? What type of substance is it? And Amy doesn't get to answer. What type of substance is it? What do you think? Conrad, what do you think? It's ionic. Remember our choices for type of substance, there's only two. It's either ionic, with a metal and non-metal, or molecular, all non-metals. This is ionic. Ionic. That was terrible. Look at what I just did there. Zip. Ionic. Type of solution. Acidic, basic, or neutral? What do you got? What's going to be? How do we know whether it's acidic? What do we have to have in order for it to be an acid? Where? On the front. Is there an H on the front? No. What do we need to have it as a base? OH at the back. Is there an OH at the back? No. It's neutral. 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 Oh my goodness. I'm losing it. Neutral. Yes, it is good, isn't it? And what type of reaction will it undergo? Yep. No, that's not true. It's dissociation. If it's ionic, it undergoes dissociation. All right? If it's ionic, because remember, they're already ions. Remember? They're the couple that I've already, how's it going? Okay, we'll see you later. I'm dissociating from you. HNO3, metal, non-metal, or all non-metals? So it's molecular. Molecular. Now, acidic, basic, or neutral? Acidic. Why? H at the front. So this is an acid. It's acidic. It's an acid. When it breaks apart, what's it going to do? Ionization. Because when it's a molecule, it's like they're holding hands, right? We've got the bond in there. This is ionization. Ionization. Why? Because when it's molecular, it's ionization. CaSO4. CaSO4. What type is it? Ionic, metal, and non-metal. Acidic, basic, or neutral? And Conrad is going to have to be cut off here, but he's right. Neutral. Doesn't have an H plus. Doesn't have an H. What's going to happen to this when it falls apart? Look at my arrows. They're guiding you. Dissociation. Dissociation. C2H5OH. Molecular because it is all non-metals. All right? Now, acidic, basic, or neutral? This is a trick one. Yeah, you're right. Can't answer. You can't answer. Conrad can't answer. Yeah, Amy, you step up on that one. What's the last one going to be? Acidic, basic, or neutral? I knew she was going to say that. No, sorry, it's not basic.
Acidic.
It's not acidic.
Neutral.
It's neutral.
Why is it neutral? No, wait.
It doesn't fall off, right? Remember we talked about these guys here, right? See here we have CH3COOH, but they're all bonded together because they're all nonmetals. This is that couple, the sweethearts, they make it all the way to the end. No dissociation. Yeah, there's all kinds of them. That's exactly one that's like it because they're all nonmetals and they're bonded strongly to that.
How do you know?
Because they're all nonmetals and they're bonded strongly to that.
But if it's muscular,
If this is a metal and a this is the metal and a nonmetal, it's ionic, therefore it's basic. If it's molecular, you got to be careful. If it starts with the H, then it's acidic. Yeah. Now, this one is neutral because it doesn't do any. It doesn't not applicable. The molecular ones that are not acids, they don't do anything. They don't fall apart at all. Okay, so there's a little practice sheet that has a bunch of compounds on it, and you can just type it in for practice. I actually didn't do solutions for it, so we'll have to take that up maybe or at the end of, or tomorrow. Let me. What's that?
you share it to everyone, but you can copy it.
Oh, you can't type it? You can't type on it? Oh, you can only view it.
And they send it to like all of us, we all have this on it.
Really?
Yeah, because I see Conrad's on it.
Oh yeah, Conrad's looking at it, but he's not able to edit it. I'll change that and I'll put it so that you each get a copy. Okay, let me stop my my video here. Yep, we're gonna now add some acid and base to that. Okay.